and thanks for the opportunity to talk. And I also wanted to thank the organizers and the Simons Institute and the people at the Simons Institute for the amazing job that you all do, considering the circumstances. I guess we all would have loved to be in Berkeley in person, but nevertheless, that is not possible these days. But I'm surprised how much I enjoy being there virtually and participating in so many things that are going on. So yeah, thank you to all of you. So what I'm going to talk about is thin shell estimates for maximal affine surface area, and I'm going to explain everything that may not be so familiar to this community. So let's start with the definition of the main object we'll be talking about. So K will always be a convex body in Rn. Then the classical affine surface area is defined as follows. So I'll denote it like so. I'll denote it like so with little AS. So affine surface area of K is what? So it is the integral over the boundary of the convex body K. So boundary of the body I'll denote like so. And then what do we integrate? We integrate the Gauss curvature kappa raised to the power 1 over n plus 1 at a boundary point x. And we integrate with respect to mu k, the usual surface area measure on the boundary. So what do I mean if I say usual surface area measure? I mean that if this function kappa were not there, the integral would just give us the usual surface area of a convex body. So this is called the affine surface area. And let me now list, or maybe let's look at some examples first. So let me make sure that you see the definition. So let's look at the Euclidean unit ball. I'll denote that like so, Bn2. So that's the Euclidean unit ball. And if we want to compute the affine surface area of the Euclidean unit ball, what do we get? Well, if we look at the definition, then we'll see Gauss curvature of the Euclidean unit ball is just 1. So we'll be integrating just over the boundary of the Euclidean unit ball. So what we'll get for the affine surface area of the Euclidean unit ball is just the usual surface area, which is n times the volume of the Euclidean unit ball. And I always denote by this, with these two parallel bars, these absolute value signs, I denote the volume in its dimension. So that's the n-dimensional volume here, and that's the n-1 dimensional volume of the surface area of the body here. So that is one example where we can compute the affine surface area. That's the case of the Euclidean unit ball. The other example that's easy to see is when the body K is a polytop P, then as the Gauss curvature almost everywhere on the boundary is 0, this affine surface area of a polytop will always be 0. So those are the examples, or two examples, and that helps us to understand some of the properties. So the first property I want to mention is upper semicontinuity. So this affine surface area is upper semi-continuous. However, if we look at these examples that we have up there, we see that we cannot expect to get continuity because we know that every convex body can be approximated, say in the Hausdorff metric, by polytops. And in particular, then also the Euclidean unit ball can be approximated by polytops. But for polytops, we always have affine surface area is 0, but the limiting object, the Euclidean unit ball, has surface area, affine surface area different from 0. So we cannot expect continuity, but upper semi-continuity holds. Now, another very nice and actually important property in the context of this affine surface area is that we have an affine isoparametric inequality, which says that look at all convex bodies with fixed volume, then affine surface area is maximized for ellipsoids. And I'll say that I'll formulate it a little bit later, more formally, but that's the short of it. There is this affine isoparametric inequality, and it's extremely useful actually because it lets us decide in many situations where ellipsoids are extremizers. It lets us decide on the extremizers. It lets us solve extremal problems when ellipsoids are extremizers. And lastly, I want to mention that it is an affine invariant, which basically is indicated by the name affine surface area. So it is an affine invariant. Let me comment a little bit on that. So if we look at the definition again, then notice, so I'm writing definition again. So affine surface area of K, it's the integral over the boundary of K, Gauss curvature to the power 1 over n plus 1 d mu K. It's this integral. And if we look at this expression, there is no reason to believe that that should be an affine invariant. It looks pretty, yeah, it's why on earth should this be an affine invariant? And to explain that it is indeed an affine invariant, or how we can see better that it is indeed an affine invariant, and also to explain a little bit the name, I give another formulation of this affine surface area, which is now completely geometric. The one that we had before was actually analytic via this integral, but well, it was realized, so by Carsten Schütt and myself, that actually this affine surface area is a variation of volume. That is, you can look at it as a derivative of volume. So how can we get this affine surface area as a derivative of volume? So here on the left is our affine surface area. So this we showed is equal to some constant Cn, which we know exactly what it is. It depends only on the dimension of this expression here. So we look at a derivative of volume, namely the difference of the volume of the body K minus the volume of the floating body. So K delta is the floating body, and I'll explain in a moment what that is. And then we'll divide by delta to the 2 over n plus 1. And we showed that this limit exists as delta goes to 0 and actually gives us this affine surface area. And so now we see why this quantity is an affine invariant, because it's the differences of volumes, and volumes are of course affine invariant. And also it explains the name affine surface area, because if we think of Minkowski's definition of volume, this definition of surface, of the usual surface area, sorry, this is also a variation of volume. So that explains the affine invariance and the name affine surface area. Okay, now I need to explain what is the floating body or the convex floating body. Actually, there's another such notion of floating body, which is going back to the like 200 years ago of a French mathematician by the name of Dupin. He also had a notion of a floating body, but this one's more complicated. I mean, Dupin's one, and not necessarily convex. So we want to deal with convex sets and define the convex floating body, which is defined as follows. So here we have our convex body K, and what do we look at? We look at hyperplanes H that cut off a set of volume delta of the body K. So the hyperplane H gives us two half spaces, H minus and H plus. So we'll pick the hyperplanes H so that the volume of H minus intersected with K is smaller or equal than delta. And then we'll take the intersection H plus of all the opposite half spaces. And if we do that, the intersection of all those half spaces H plus for every possible position of a hyperplane H, we'll get a convex body that sits in K, and that we call the floating body. So it's floating body is always a subset of the original body, and it's convex because it's arbitrary intersection of convex sets. Of course, we have to pick delta sufficiently small that like it shouldn't be bigger than say half the volume, otherwise we would get the empty set. So we want to take delta such that we can expect that things make sense. Good. So that's giving us a little bit better insight on this affine surface area, but I want to mention one more thing to explain why this quantity is important and why we really want to understand it better. I've given one reason already, which were this affine isoparametric inequality, which, as I said, is a great tool to decide on extremal problems if the extremizers are ellipsoids. There is another situation that I want to mention where this affine surface area plays a role, and that is in approximation of convex bodies by polytops. So let me explain the setup. The setup is as follows. So we want to, so we have a convex body K. Now what we'll do is we choose at random capital N points on the boundary of K. So we choose those points here on the boundary of K with respect to a probability measure, which I call PF. So what's PF? It's just the surface measure hit by a function F that's positive, and yeah, so hit by a positive function F. And we want a probability measure. Then having chosen these capital N points on the boundary with respect to this measure, we'll take the convex hull of these capital N chosen points, and that gives us a polytop or a random polytop. And one of the natural questions that one asks in this context is, what is the expected volume of such a random polytop? So we'll look at this question, and actually we'll look at an equivalent formulation of the question, which is, okay, what is the volume defect between the volume of the body and the expected volume of such a random polytop? And that is as follows. So here we'll have this volume defect between the volume of the body K and the expected volume of a random polytop P, where we have chosen capital N points on the boundary of F of K with respect to this probability measure PF. And now we have picked the right F, and I'll explain a little bit what I mean by this. So we look at this volume difference, which is the same as, you know, deciding what's the expected volume of such a random polytop. And then if we divide by this quantity here, that is the number of chosen points to the power minus 2 over n minus 1, and we let the number of chosen points go to infinity, then we can show that this limit exists and is equal to, now I have called the constant in the same way as I did in the previous theorem. It's not the same constant, but we know exactly what the constant is, and it's just depending on n. So we'll get a constant that's depending on n times this affine surface area raised to the power n plus 1 over n minus 1. So it's this affine surface area that comes in naturally in approximation of convex bodies by polytops. In fact, if we think about it, this is not so surprising that this affine surface area should play a role in such situations, because what this affine surface area does, in a sense, it measures the boundary behavior of a convex body. And if we think about approximation, then intuitively it's clear where the boundary of the body is flat, to get the same good approximation in the symmetric difference metric, which is the one that we are using here, we should put fewer points where the body is flat to get the same good approximation, and we should put more points where the body is very curved to get the same good approximation in the symmetric difference metric. So it's kind of not too surprising that this affine surface area comes in such approximation questions, as it's closely related to the boundary structure of a convex body. Now, there is one amazing thing that I want to mention about this result that I've mentioned here, which is the following. This random approximation here is almost as good as best approximation. So what do I mean by that? I mean, if instead of looking at the volume difference of K, that is the volume of the body, and such expected volume of a random polytop, if we replace this by the volume of a best approximating polytop, so I replace this by the volume of a best approximating polytop with n vertices, chosen also, oh, not chosen, they are not chosen. So if I replace it by the best approximating polytop with n vertices, I look at exactly the same limit with exactly the same number here. Then one can show that this limit also exists and gives another constant, say dn, and again the affine surface area with the same power, n plus 1 over n minus 1. So the only difference between this random approximation result and the best approximation result is in this constant. And of course, because you have best approximation, the constant, well, let's call it dn, the one that comes from the best approximation, dn is of course smaller or equal than cn. But actually, surprisingly, not by much, only by 1 plus log n, oh, sorry, only by log n over n dn. So in particular, as the dimension is large, we see that that quantity is really small. So then even in these constants that depend only on the dimension, this best approximation and random approximation do really not differ by much. Okay, so that was to give you a bit of an idea why one really wants to look at this quantity, this affine surface area. And let's now move towards what we want to discuss a little bit in more detail in what will follow.
Can I ask, what is the f? You told us you're going to tell us what the right choice of the function f, of the density.
Oh, okay. So yes, what's the right choice of the function f? Yes, that's of course good. So the right choice of the function f is if you do what I tried to explain, if you choose the points according to curvature. So the function f would be connected to the Gauss curvature of a boundary point.
I see. So like, if there is more curvature, you sample more points. So it will be like
exactly.
inversely
If there
proportional.
is more curvature, you sample more points.
Got it.
Yeah.
Thank you.
But basically, we have the result for any function f that is positive and yeah, has some continuity properties, strictly positive and some continuity properties. And yes, that was, I was always also hoping that, you know, there are so many people that are in Berkeley now with so much knowledge about things in algorithm and computer science. So I had been hoping that maybe one can, you know, even develop kind of an algorithm for such approximation problems with a choice of a function. And that would also, you know, give us a way maybe to compute this affine surface area in more cases of convex bodies, because it's really notoriously difficult to compute because curvature is not an easy expression to handle for a general convex body. Yeah, but okay. Yes, so thanks for the question. So now what do we want to talk about, or what do I want to tell you about after, you know, just, you know, explaining why this affine surface area is interesting, or trying to explain why this affine surface area is interesting? We want to deal with this issue of upper semi-continuity. We already saw it cannot be continuous, this affine surface area, but it is upper semi-continuous. And actually, then would it be possible, is the question, that we get a continuous affine invariant? That is something that still has all the nice properties as the affine surface area, but is not just upper semi-continuous, but in fact continuous. And this we can do by defining what is called the maximal affine surface area. So I'll denote this maximal affine surface area like so. So I'll just use capital letters AS instead of the small letters. So how is it defined? It's the sup over all little affine surface area of C, where we look at all convex bodies C that are contained in K. And one can show that the sup is actually a max and it is attained. So it's maximum over all convex bodies C in K of affine surface area, little affine surface area of C. And it is attained for, one can show that it is attained at a convex body. Sometimes I call it K0, sometimes I call it C0. So by continuity and, not continuity, but upper semi-continuity and compactness, this sup or this maximum is attained at a given, at a specific body K0. And then, having defined this maximal affine surface area, one can actually show that this is continuous. I don't want to, this is pretty easy to see, and I do not want to dwell on that too much, but it is continuous. Let's look at an example now, what we can expect. Now, for instance, in the case of polytops. And as polytops, as a polytop, let's take the L infinity unit ball. So, so L infinity unit ball is just here is 0. It's just the n cube with side length 2 centered at 0. And if we now compute this maximal affine surface area for this L infinity unit ball, then we see, okay, we do find the Euclidean unit ball in there. So for sure, we know that this maximal affine surface area of the L infinity unit ball is bigger or equal than the affine surface area of the Euclidean unit ball, which is n times the volume of the Euclidean unit ball. And it's actually equal to that. So for sure, it's not 0 as it was before when we just were looking at the usual affine surface area. So now for polytops, the maximal affine surface area is actually also positive. Okay. Let me tell you a little bit what is known about this maximal affine surface area. And surprisingly, the only things that are known are things the only things known are for convex bodies in the plane. So the first result I want to mention is a theorem due to Barani and Werschik in the case of the square in the plane, and due to Barani for general convex body K in the plane. What this result says is that, okay, we already know that from what I mentioned previously, that there is a convex body C0 in a given convex body K for which this maximal affine surface area is attained. So I've now called this body C0. So this is the body where the maximal affine surface area is attained. And what this theorem of Barani and Werschik, or Barani, says is that this body C0 is unique. This result is only known in the plane, and we do not know if this is true in dimension 3 or higher. The next one I want to mention is again a result due to Barani and Werschik for the square, and due to Barani in the case of a general convex body, again only in the plane. Before I can do that, I need to introduce some notation. So we look at K, a convex body in the plane, and then by this script P sub n of K, I denote the set of all convex polygons that are contained in K, where we pick the vertices from the lattice C squared over n, where n is a natural number. So I have a picture here, looks like so. here is our lattice grid. Here is our convex body K in the plane. We'll pick points on the lattice inside the body K. We'll take the convex hull and we'll get a lattice polygon. Then there was a question by Werner, who asked, well, is there a limit shape amongst those convex polygons contained in K that are picked from the lattice? And what's meant by limit shape is explained in the theorem that I mentioned next. So it's again due to Barani, as I said, and Werner in the case of the square, and Barani for a general convex body K in the plane. So what does it say? It says that, okay, that the limit as the lattice grid gets finer and finer, that is as capital N goes to infinity, so lattice grid gets finer and finer, of this quantity here, the limit of this quantity here exists and is equal to 1. So what do we have in the bottom? We'll have, now it's a slight use of abuse of notation, because this noun of course doesn't denote volume, it just denotes cardinality. So this means here we look at the cardinality of all lattice polygons that are contained in K. That's what's on the bottom here, and on top here we look at the number of lattice polygons in K where the vertices are picked from our lattice grid that are epsilon close in Hausdorff distance to this set C0 that has maximal affine surface area contained in K. And what the theorem says that as the grid gets finer and finer, almost all, let's formulate it like so, almost all lattice polygons are epsilon close to this maximal affine surface area set inside the body K. And that's what's meant by limit shape. So in this sense, C0 is the limit shape of these lattice polygons as the lattice grid gets finer and finer. And again, that's a result, that's a very pretty result, very beautiful result in the plane, and we do not know if such a thing holds in higher dimensions. And that's basically, so that's basically all that is known about this maximal affine surface area. And the things that are known are basically happening in the plane. And so we were curious if we could say, or what we could say possibly in higher dimensions, and if it were possible to say something at least on the size of this set, this maximal affine surface area now for a convex body K in Rn. So that was what we were starting to look at. And I need, before I can formulate what we got, I need to introduce again some notation, but that should be, that now should be familiar to everybody in this community. So, what's the notation that I'll be using? So from now on, we'll always be looking at a convex body K that has barycenter or center of gravity or centroid at 0. We can do this because the quantities that we'll look at are all affine invariant, so it doesn't matter where I position the body in space. So we can assume without loss of generality that the barycenter is at 0. I'll also be needing the isotropic constant, Lk. I don't think I need to explain what that is. Everybody is familiar with this. So by Lk, I'll denote the isotropic constant. And of course, we all know that it's an open, important open problem in convex geometry and many other areas if it's really a constant. And the best known result so far is due to Boas. So I don't need to go into details here. Now let's look at the result that we could show now for a convex body K in dimension n, that is K is a convex body in Rn. what we can say about the size of this maximal affine surface area. And that's one of the results we have that I want to Giladi, Han Huang, Carsten Schütt, and myself. So what does it say? Here it says that, okay, so let's look at what's the quotient that we are looking at here. So it says maximal affine surface area.
Is anyone else having problems with the audio?
Yeah, I do.
Yeah, me too. I assumed it was on my end because I usually have problems.
Elisabeth, I think it's the audio is coming in and out.
Oh, okay. What can we do?
Do you is there a way to move closer to your wireless router, or?
Okay.
Actually, right now it's okay. Right now it's okay. So maybe try again.
Okay, I'll try again.
It might also help just to turn off your video.
Say again.
It might help us if you turn off your video, actually.
Oh, okay. Now I did something not good.
So actually, I can turn off your video and then maybe we try if the audio improves.
Now it's gone. It should be gone, right?
It's okay for now. Yeah, go ahead.
Okay. Is it okay now?
I think it's okay for now. Yeah.
Sorry about that.
Sorry for the interruption.
No, that's fine. That's fine. Yeah. And please let me know again if there is a problem. Then I try to get closer to the router. Yeah. So you guys let me know when there is a problem again, right?
Yeah, we will. Thanks.
Okay. Thanks. Okay. So we look at this quotient here. It's bounded from above by 1, bounded from below by, okay, the isotropic constant comes in, it gets raised to the power 2n over n plus 1. If we believe that it's a constant, then we would just have a constant here. C is an absolute constant, and then we still have a dimension dependence on the lower bound, so n to the 5 over 6, which is a bit, yeah, not what probably should be there. So there should be probably something else there. But that's where we are at the moment. And let's have a closer look at this quotient here, which actually, so to really understand what's the order of magnitude, what we are looking at here. So we have n to times the volume of the Euclidean unit ball raised to this power. This is of course of the order of a constant, because Euclidean unit ball raised to the power 2 over n plus 1, this is just 1 over n modulo a constant. So that expression here is just a constant. So it says that the expression that we are looking at here basically behaves like a power of volume of K. So basically what this says is that this maximal affine surface area behaves like a power of volume, namely volume to the n minus 1 over n plus 1 modulo this lower bound where we still have the isotropic constant around and this factor n to the 5 over 6. So that's basically what we want to get out of this estimate, or to understand what's the order of magnitude of this estimate. And now let's look a little bit at how we can prove this inequality. The right-hand side, so that's the inequality. The right-hand side of the inequality is actually sharp, and its equality is attained if and only if K is an ellipsoid. So I have written here, it's attained, for instance, for the ball, but equality holds if and only if K is an ellipsoid. And I can give a very quick proof of the right-hand side of the inequality. That's the easy direction. And that just follows from what I told you earlier, the affine isoparametric inequality. And I now give a formal a statement of the affine isoparametric inequality. So what does it say? It says the affine surface area, it's the little affine surface area here. The affine surface area of a convex body K is smaller or equal than the affine surface area of the Euclidean unit ball times the volume of K divided by the volume of the Euclidean unit ball. And we raise everybody here to the power n minus 1 over n plus 1 with equality if and only if K is an ellipsoid. This is the affine isoparametric inequality. And by the way, for this maximal affine surface area, we have the same affine isoparametric inequality holding. Now, this gives us immediately the upper bound, because what do we have to show? Maybe I'll stop here. Maybe you guys want to see, yes, let's see the inequality. So here we'll have the maximal affine surface area that we are looking at now, which by definition is the little affine surface area of all convex bodies C contained in K. Now to this little AS of C, we apply the above affine isoparametric inequality. So we'll get that this is smaller or equal, nothing has changed with the maximum over C, but then we use the inequality. So we'll get affine surface area of the Euclidean unit ball times volume of C divided by volume of the Euclidean unit ball raised to the power n minus 1 over n plus 1. And then we estimate simply the volume of C by the volume of K. And we remember now in the next step that the affine surface area of the Euclidean unit ball is just n times the volume of the Euclidean unit ball to get our upper bound. So that was really nothing much. It was just the use of this classical, so to speak, affine isoparametric inequality. Okay. Now for the left-hand side, so it's for the left-hand side, we have to do some work. So what do we have to do to get the left-hand side? Well, we'll have to find a good K-twiddle, a convex body in K, for which we can compute this little affine surface area of K-twiddle to get the estimate that we want. That is to get, well, K-twiddle is a convex body contained in K. This maximal affine surface area consequently is always bigger or equal than the little affine surface area of the K-twiddle. And we want to find a K-twiddle so that our desired estimate holds. Now, thinking about that there is this affine isoparametric inequality, a natural first candidate to think about, to take as the K-twiddle, would be something related to the Euclidean unit ball or to an ellipsoid. So first natural idea to pick would be maybe if we take the as K-twiddle, the ellipsoid of maximal volume contained in K, maybe that would be a good candidate because we know from the affine isoparametric inequality, ellipsoids or unit balls do give us maximal affine surface area. So let's look at an example to try to see that if that works. So here I have written what's the ellipsoid of maximal volume. That goes back to Fritz John. It says that if a convex body K is given in Rn, then there exists an ellipsoid, which I've called E0, of maximal volume contained in K, and it's also unique. So let's look at the example of K being the L infinity unit ball. I have drawn it again here. We know that the ellipsoid of maximal volume contained in the L infinity unit ball is just the standard Euclidean unit ball. Also, we know that the isotropic constant of the L infinity unit ball is just a constant. So what would we get? If we picked as our K-twiddle to get our lower estimate, what would we get if we picked as K-twiddle this ellipsoid of maximal volume, which is just the Euclidean unit ball? Well, we would get the following. So we look at our maximal affine surface area divided by the volume. That's the expression that we basically want to compute now, divided by the volume raised to the power n minus 1 over n plus 1. So this is bigger or equal than, now we pick the ellipsoid of maximal volume, and okay, then we'll have the volume of the Euclid of the L infinity unit ball, which is 2 to the n. Well, now I would have to raise to the power n minus 1 over n plus 1, but if n is large, dimension is large, that's just the modular constant. So now we know that the affine surface area of the Euclidean unit ball, which is the one that we pick here as our maximal ellipsoid of maximal volume, this is just n times the volume of the Euclidean unit ball. Well, we have this divided by 2 to the n. So what we'll get is, if one computes that, we'll get just a constant over 2 to the n times n to the power n over 2, and that is much too small, because what we really want to get is n to the 5 over 6 and not n to the n over 2. So, so this ellipsoid of maximal volume is not giving us the good lower estimate. So we have to do something else. So let me show you what is the something else that we will do. And so let's first position the body in the convex body that we are dealing with. Let's position it in a way so that we can deal with it nicely. What we'll do is we'll put the body in isotropic position. So volume is 1, center of gravity will be at 0, and we'll assume that the isotropic constant that is given to us like so, that is, the position is like so, that isotropic constant can be computed as indicated here. Oh, I should have said by these double bars, I denote the Euclidean norm on Rn. So now we've placed the body in isotropic position, and what we'll do next is I will not show the proof in the most general, or actually I'll give an indication of the proof, but I'll give an indication of the proof not in the most general situation, but only under the assumption that the isotropic constant is indeed a constant. Then I don't have to carry this LK with me all the time. Assuming now that the isotropic constant is a constant, so that I don't have to carry it with me all the time, what do we need to show the lower bound? Well, the quantity that we want to bound from below is this one here. So maximal affine surface area of K divided by these expressions here. But we've already seen that n times the volume of the Euclidean unit ball raised to the power 2 over n plus 1, this is just a constant. Also now, as we are in isotropic position, we know that the volume of K is 1. So basically what we'll have here is just modulo a constant, the maximal affine surface area of K. And this we want to bound from below. That's what we need to show by a constant divided by n to the 5 over 6. What I'll try to indicate is not striving for the best exponent. So instead of 5 over 6, I'll indicate how we get to the exponent 1. So how do we do this? What we will use is, now comes this other thing that was in the title. We'll use a thin shell estimate that is due to Grigoris Pauris and Olivier Guédon and Emmanuel Millman. What does this thin shell estimate say? It says that there are absolute constants. There is an absolute constant Z0, so that if we look at the volume of all those points x in K that have Euclidean norm strictly bigger than this absolute constant Z0 times root n times isotropic constant times t, this volume is small, namely smaller or equal than e to the minus root n times t. And that for all t bigger or equal than 1. Okay. So let's specify things a little bit. Namely, let's take t equals 1. And then let's recall that we are in the situation where we want to assume that the isotropic constant is a constant. What is it that we are actually looking at when we are looking at this thin shell estimate? We are looking at the volume of all those x in K that have Euclidean norm bigger or equal than another absolute constant C twiddle times root n, and we know this volume is small, so it's smaller or equal than e to the minus root n. So if we draw a picture, then what it means, so here is our convex body, here is our ball with radius C twiddle root n. And what this estimate here says that, okay, the volume that is outside this ball with radius C twiddle root n, but still in K, and this is this red set that I have indicated, this volume is small. That is what this estimate above says. Okay. On the other hand, we know if we look at the volume of all those in X, of all those X in K for which the Euclidean norm is smaller than a constant, absolute constant C1 times root n, and C1 we will choose appropriately, so we look at this volume, that's of course trivially smaller or equal than the volume of the whole ball with radius C1 root n, which is C1 root n to the n times the volume of the ball, which is of the order C1 to the n times n to the n over 2 coming from here, and then comes the volume of the ball, modulo a constant, it is also n to the n over 2. So if we choose the C1 accordingly, we can make this smaller than 1/8. So this volume here that is inside the ball with radius C1 root n, where the C1 is chosen, right, is also small. So this says that with the proper choices of C1 and C2, the volume that is in this annulus or in this thin shell around square root of 2, this volume can be made large, namely bigger than 1/4. So norm is bigger or equal than C1 root n and smaller or equal than C2 root n, and this volume is bigger than 1/4. This is what we can achieve choosing the constant C1 and C2 in the right way. Okay, so what we now do to get our estimate from below is that, remember, we still want to choose a K twiddle that is doing for us the job to get the estimate from below for our maximal affine surface area. What we'll now do is we choose as the K twiddle K intersected. We have to intersect with K because we want to stay inside the convex body K, and we intersect with a ball that has a radius R, where the R is chosen suitably within this annulus. So I've made a picture. We have our body, okay. We'll have our annulus that's given to us by the small radius C1 root n and by the large radius C2 root n. So here is our annulus. And now we'll choose R right. That is, we choose a radius R so that we are placed within the annulus and intersect with K. So that is this red, the convex body that I have indicated in red here. So that is the K twiddle that we'll take for getting the lower bound, and that gives us, in fact, the lower bound. Maybe I should say something why one comes up with such a construction. And there are basically two reasons why we came up with such a construction. One was, so to speak, a pragmatic reason, which is that, and I have said that before, basically there are not so many convex bodies for which we can compute the affine surface area for, because of the Gauss curvature involved in the thing. It's notoriously difficult to compute affine surface area, and we can do it basically only for balls or ellipsoids or polytops. So that was the pragmatic reason for us wanting to bring in the boundary or parts of the boundary of the Euclidean ball. Now, the other reason is as follows. It's because of this affine isoparametric inequality, we still do want to bring in the Euclidean ball or an ellipsoid, because this inequality tells us that affine surface area is maximized for Euclidean balls or ellipsoids. So we do want to have that somehow present. And then if you think about what I said, is how do we get affine surface area for the Euclidean ball? Well, affine surface area for the Euclidean ball is nothing else but the usual surface area of the Euclidean ball, which is n times the volume of the Euclidean ball. So now we have a result which tells us that volume is concentrated or volume is big within an annulus. So we suspect that, oh, okay, maybe maybe surface area and consequently affine surface area will also still be big within such an annulus. So that was the thinking why we picked these thin shell estimates, and we're hoping that it would give us a better result. Thing is, as I tried to indicate, one has to be a little bit careful which radius one chooses within this annulus. And in order to make things work, what we'll have to do is we'll actually have to subdivide this annulus A into smaller subannuli that I have written here. So we'll subdivide it in subannuli Li, where I runs from 0 to K. So what's K? Where do we stop? Well, K is the, how do you say, floor? It's
integer floor.
Yes, it's the biggest integer that's smaller than that. Okay. Integer floor. I never, for the life of me, I cannot remember. I never can remember how to call this thing.
Yeah, I think
it's the floor of this number here. So it's n log to the base 2 of these constants C2 and C1 that we have. But you'll see the order, because dimension is typically large, it's actually of the order n. So that's where we end with the subdivision of our annulus. What do we actually have? Well, if I is equal to 0, then we'll just end up at, because we march through the annulus in steps of order, maybe I should show the previous one. So we'll march through the annulus in steps. So I is equal to 0, we'll start at C1 root n. And then we march through the annulus in steps of order 2 to the 1 over n. And so for I equals 0, we'll just start at C1 root n, that is at the lower point of our annulus, and we'll go up to C1 root n 2 to the 1 over n. And as we march through the annulus, we'll end up with our I being k, which is this number here. So we'll end up at C1 root n 2 to the n log base 2 C2 over C1 over n. So n goes away. As it's log to base 2, we'll end up here. So the C1 goes away. So we'll end up exactly at the upper part of our annulus. And then we'll march a little bit below. So this tells us that actually A is contained in the union of these annuli. And as K is roughly n, and as the volume of A is big, namely bigger than 1 over 4, we know that there must exist at least one I0, so that the volume of Li0 is bigger or equal than 1 over C times n, and C can actually be taken to be equal to 4. Maybe I should go a bit slower now, because now it's the technical part. So okay, so we are almost there. As the K twiddle, we'll put now K intersected with the Euclidean ball where we have picked as the radius R, and I've called it R1 now, of this subannulus that corresponds to the lower part for this I0. So that is our R1. It's C1 2 to the I0 over n root n. That is the R that we pick. And then, of course, trivially, K twiddle is contained in K. And let me just show you 2 steps, because I'm seeing that I'm a bit short of time. Let me just give you an indication how we now compute this affine surface area of this K twiddle. So I have written the definition again. So affine surface area of K twiddle. So it's just the definition. It's the Gauss curvature raised to the power 1 over n plus 1. We integrate with respect to the usual surface area, measure mu, and we integrate over the boundary of K twiddle. Nothing has happened here. I have just recalled how the K twiddle was defined, namely as the intersection of K with this ball with radius R1, where we have chosen the R1 so that we are within the annulus. Now, instead of integrating over this whole boundary, we only pick those parts of the twiddle that correspond to these parts of the ball with radius R1 that are in K. So we only perform integration over that. And there we know what the Gauss curvature is. The Gauss curvature is nothing else but R1 to the minus n plus 1. So because we know what R1 is, it's C1 2 to the I0 over n root n, and this to the minus n minus 1. So that is our R1. So we get that this maximal affine surface area is bigger or equal than comes our radius, which is this, but it needs to get taken to the power 1 over n plus 1 as well, times the remaining surface area, that is the surface area of these parts here. That is the surface area of K intersected with the surface of this ball with radius R1. Now, if you look at this quantity here, then you'll see that that's actually because 2 to the I0 over n, that's basically a constant. So what this quantity, or what's the order of magnitude of this expression here, is just constant over square root of n. Now, what we'll have here is something that we still have to compute, but now I claim that this surface area can be estimated from below by another constant C twiddle times root n. And if we have this claim, then actually our maximal affine surface area, which is bigger or equal than the affine surface area of K twiddle, will be bigger or equal than this first C over root n times C twiddle over root n, which is C over n, which I wanted to give you as a lower estimate because I didn't want to strive for the best exponent, which is 5 over 6. And I guess I should stop because yes, so thank you very much. I'll not go over the other things. I'll stop here. Yeah, thanks.